What up, everybody? Thank you for joining me for this episode. I have another great conversation for you. This episode, I traveled to Frankfurt, to the Frankfurt Institute of Advanced Studies, to speak with Sascha Vogel. Sascha's a great guy. He's not really involved on a day-to-day basis in the research in the lab that's going on at the Institute, but he's very knowledgeable of basically all the projects that are going on there. And he did his doctorate in physics, so he's also very knowledgeable in physics. He schooled me on some of the things that were going on there, because if you listen to this show, you know I am completely ignorant of physics. So we talked a little bit about that. We talked a lot about science communication. Again, I know that's becoming quite a theme here on this show, but it was fun because he's, like I said, a really interesting guy, easy to talk to, and he's quite involved in science communication. He runs a small company website called sciencebirds.de, where basically you can go there and sort of hire him for one of his shows that he does. He has a number of different shows that he does, or lectures that he does. He can prepare things, specifically for the event that you're doing, or just come and speak. He does a Physics in Hollywood series, basically, breaking down the physics in different movies and stuff like that. So some of it is in English, a lot of it is in German, but I don't know, sciencebirds.de is worth checking out. I first met him after I saw him speak at the March for Science in Frankfurt, and we talked a little bit about that, but he's really kind of the first guy that I reached out to when I moved here, to sort of get in touch in the sort of science communication field. I was still doing my PhD at that time and looking to get into doing science writing, journalism, communication, all that good stuff that I do now. And so having him answer my email and invite me to this workshop was really, really great. Sort of big thank you, Sascha, for doing that. And then thank you for coming on the show and chatting with me for an hour or so. I'll kind of leave it there. I don't want to go too much into what we talked about. It's a really great conversation. I hope you enjoy it. I hope we can do it again. Frankfurt's not too far from where I am, and so hopefully Sascha and I can sit down and do this again, because I really, really enjoyed it. And there's lots of really great research going on at the Frankfurt Institute of Advanced Studies, which we didn't get to touch on. And so I'd love to go back there and, maybe speak with some more people or speak with Sascha again. But yeah, leave it at that. Let you enjoy this conversation. As always, the freaks are going to bring us in. And then it's on to my conversation with Sascha Vogel. Do my little podcast here. So
thanks for inviting me.
Yeah, no problem. I mean, I guess we could give a little bit of context too. Is that we have met before.
We did, yes.
Yeah, you organized it was a workshop, sort of week.
It was a workshop called Interdisciplinary Science Communication.
Yeah.
Last year, 2017.
Yeah, and that was here at the Frankfurt Institute of Advanced Studies.
Exactly.
Yeah, and I thought it was really nice. I mean,
it was quite nice. So we got in contact with lots of people. Actually, I guess usually don't get into contact with each other. We had scientists from various areas. So mostly natural scientists, but also some from other areas. And we had people from politics even. So you remember
that's right. Yeah.
From the Bayerische Amt für Umweltschutz, so it's basically the Bavarian state environmental agency, something like that. Yeah. Trying to figure out how to actually talk about their stuff they're doing. So it was a quite good mix.
Yeah. No, it was great. And for me too, like I had like more or less just arrived in Germany and had ambitions of doing science communication stuff. So it was really great for me. But yeah, so it was at the Institute of Advanced Studies, which is where we are now. And I was just taking a look at the website that, like you had sent me, like this is the sort of research that's going on. And it seems like how much of it, I guess my question is, how much of the research is application based, and how much is it within the different programs sort of feeding off one another? Because the topic range is quite wide.
Yes.
Neuroscience, I saw some economic stuff, computing, physics, biology. So when it's advanced studies, is there a gearing it towards application?
No, absolutely not.
It's not.
Absolutely not. So it's all fundamental science.
Yeah.
So the idea was, like, what is it now, 15 years ago roughly? You have all the programs where experimentalists, especially in physics, so the founder was a physicist, or one of the two founders was a physicist, the other a neuroscience guy, said, okay, we have all those programs where experimentalists get together and have, collaborations, and nothing exists like that for theoreticians. So the idea of the Frankfurt Institute for Advanced Studies was you get together theoreticians from various fields, so mostly at that time physics, biology, and chemistry, so neuroscience as one of the main driving forces, and do fundamental science. So over the years, so we had a lot of high performance computing coming in, a bit of economics. You said there was a scholar paid for that. And currently, though, we are doing mostly physics, neuroscience. Those are let's call it two big blocks. So what we call life sciences is coming more and more. A bit of economics, but it's all fundamental science.
Yeah.
So machine learning is currently coming in because it's basically a gap or a bridge between the disciplines.
Yeah. Well, and that's something I'd like to get to, but. So the institute was sort of, it had this idea of fostering collaboration, or bringing all these things into one, which is interesting because, well, I didn't know that, and it's a good point, like you said, a lot of the application people have this already, and so you've been, well, you might not have been here for 15 years, but
certainly not.
But
actually, small anecdote, I experienced the founding of the institute. Because of the founder, Walter Kreiner, he died, I think, 2 years ago.
Yeah.
He was a theoretical physicist. And I was in his lecture while he founded the institute. And he always told about the progress. And it was actually quite fun. Yeah.
And that's, you did your graduate work in physics, right?
Yes.
In theoretical physics?
Theoretical physics and heavy ion physics, basically.
And so is that one of the things that's going on here?
Yes, actually, yes. So we are... Yeah, that's actually, Walter Kreiner was one of the main driving forces in Germany concerning heavy ion physics. So of course heavy ion physics was one of the topics in FIAS.
So is it, let me get, because I'm ignorant to physics.
Okay.
Heavy ion physics.
We'll change that.
Yeah, heavy ion physics. This is in the same vein as particle physics. It's
a dirty particle physics, it's called.
So you're
some people call it
working with larger. This isn't the type of thing that they'd be doing sort of at the big colliders.
Oh yeah, they do.
Okay.
So, but instead of having like a proton and a proton basically smashing together, that would be particle physics. We do it with heavy ions, as the name suggests. So we basically take for whatever gold and smash them together and see what happens, or lead, or some people use uranium. And, well, it's also done at the Large Hadron Collider. So you have the four big experiments, which is CMS, Atlas as the two main big ones. They're doing particle physics mostly. But they also have a heavy ion program. The LHCb, and there is ALICE, which is a Large Ion Collider experiment. And they basically exclusively do heavy ion physics at the LHC.
And that's one of the things that's happening here. But so what's the goal? Like, you smash gold and gold together. What are you looking for?
So basically, you try to understand what happens. So the main
I mean, that's
idea.
Science, right? You try to understand what.
So the main idea is when you start with proton at such energies, you always want to find new particles and understand the processes
this
in
is like
detail.
The quarks, and they find all that kind of stuff.
We have that as well. But what you also want to do is when you, for example, use gold on gold, you have a small medium formed, and that medium is basically, as you call it, deconfined. So what happens is, instead of having the singular protons and neutrons and whatnot, you have one big soup of quarks and gluons. So usually the quarks and gluons, so the constituents of protons, for example, or particles in general, they are bound into the particle. It's called confinement. So they are theoretical concept, or natural concepts, binding them into a particle.
Right.
And if they try to get further than, for example, usually like 1 Fermi, so 1 femtometer, they get basically sucked back into the particle.
Right.
So
this is what keeps the particle together.
Exactly.
Right.
That basically gives you the size of the particle.
Right. Yeah.
However, if you smash enough of them together, high enough speed or high enough with high enough energy, you basically, they all overlap and you get a big soup of quarks and gluons. And that's basically let's call it a new state of matter, the quark-gluon plasma. And if you actually go back in the history of the universe, like shortly after the Big Bang, and shortly means something like whatever 10 to the minus 5 seconds, so
very shortly.
Very shortly after. Well, depending on what time scales you're working on. Right. For some particle physicists, that's like,
for the guy waiting for the train, it's
exactly
incredibly short.
So roughly 10 to the minus 5 seconds after the Big Bang. That's basically the state the matter we had in the universe. So we're basically going back in time when it comes to the universe.
Yeah. And so then at this level, like you smash gold and gold or lead and lead together, so they're no longer, if I'm understanding correctly, it's no longer like each particle in what was the gold exists as a single particle. They're all sort of this mixture.
Exactly. It's a plasma.
It's a plasma, right?
The quark-gluon soup, some people call it as well.
Yeah. And so after the Big Bang, when there was high energy, all of these sort of things, that's what existed. And so then the idea is then you can take a look at how matter formed
exactly. So
the universe.
One of the things we certainly can say, because we observe it all the day, is you never see a single quark or gluon. It never has been observed. So they always, in some shape or form, they recombine or form it's called hadronization, where you basically go from quarks and gluons to hadrons. Hadrons are basically particles like protons, neutrons, pions, whatnot. So basically, is it like it's particles.
Yeah, so the ones that people are familiar with.
Exactly, the usual, the non-elementary particles.
Yeah.
And what you want to understand, for example, is how does that work? How do you go from a soup of quarks and gluons, which had to exist at some point in the universe, because you did not start out with, okay, here's a planet.
Yeah.
You went from, okay, here is a gas cloud. Okay, what does a gas cloud consist of? Okay, we need single particles, so like atoms. Oh, atoms also consist of something. How did we get there? So we had a core and the electrons. Okay, how did we get the core? Oh, the core is protons and neutrons. How did we come to the protons, and so on? So we're basically trying to understand how matter formed. So and this is basically on a very early stage. So you have quarks and gluons. How do we go to the next step in the line?
Yeah.
And so far, I mean, there are a couple of good ideas, but on a very basic, on a very fundamental level, it's not really understood yet. Which is funny.
Yeah. I think sometimes it's with physics, and I mean, physics is one that I think everybody, myself included, likes to hear about, likes to sort of talk about, but it's very difficult because these concepts are very foreign to people. You're talking about time scales that are, very small, and, the breaking of matter and particles and all this stuff. And it's really easy to get wowed by it, And I guess my question or my thought is, like, how much do we know? Like, in some senses, it feels like we know nothing, but in other articles or whatever I read, people will be like, well, we got a pretty good idea of, the Big Bang is pretty much a certainty and all these things. So where would you fall out on that?
It's, especially in science in general, but I can talk for physics because that's why I know it.
Yeah.
You never really know, I would say. So,
right. Yeah.
I mean, whenever say, this and that works, somebody comes around the corner and say, I have a new theory, and 100 years later you say, okay, we were not quite sure at that time. I mean, So, but in physics, I always say to current knowledge. So it might be completely different in 200 years, and everybody laughs at us like, "Oh, look at the guys in 2018. They didn't know about this and that." Just as we look back and like 300 years ago and say, "Oh, Newton, he didn't even know quantum mechanics." He couldn't have. That's fine. So, but to current knowledge, we have a pretty good grasp on about 45% of the universe. So that's what we call the observable matter, the baryonic matter, as we call it. Which are the particles I just described, the protons, neutrons, and so on. So basically, the thing we consist of.
Right.
The stars, galaxies, people.
All the elements we've discovered.
The elements, hydrogen, carbon, and so on. So we know about that. We know that there has to be more. And why do we know that? Because we know that gravity is a thing. So that certainly works. Everybody hopefully agrees.
I don't know. We haven't gone to some corners of YouTube yet. We might find.
Let me check outside the window. There is nobody floating.
Yeah.
So the gravity works, and also gravity works on a cosmological level. So basically, just by looking at how planets and stars and so on and everything moves, so we know that there has to be something, otherwise things would move differently.
Right.
However, we don't know what that is. And there are certain observations, for example, the WMAP experiments and so on, where you can get a good idea of how it should be distributed and so on. But it's called then dark matter and dark energy.
Right. This I've heard of.
Yeah. Exactly. For example, that's what the LHC is looking for. For example, particles which could be what we call the dark matter candidate or dark matter candidate. Sorry. But so far nothing has been found.
Right.
Which is interesting enough.
Yeah, that one always kind of freaks me out, and but again, it's the sort of like tip of the spear sort of. This is the great unknown. But it's basically, so you have these equations that show how things move, and so we can use those equations to predict, planetary movements and all this stuff based on gravity. But in order for those predictions and equations to work, there's like this unknown variable.
Exactly.
Right. And that's what we term dark energy or dark matter.
Dark matter and dark energy.
Yeah. So then.
But we call it dark because we don't know what it is.
Yeah.
Let's be blunt here.
Yeah, I guess even when you put a name on it, people might think, oh, well, we have some sort of idea, but there really is no...
I mean, there are plenty of ideas.
But nothing...
I mean, theories, it's...
Right.
But physics in the end is an empirical, an experimental subject. I mean, in the end, you need an experiment which says, this is it.
Yeah. But if it's something, so foreign to the we have, but I guess it's the same. Newton wouldn't be able to understand what a particle was or what a neutron was and all this stuff. So for us, we're looking at this thing and we've got a really good grasp of matter that we can see, or that we can not see, but observe with the certain instruments. So it just seems to me that it's how do you know where to even look if it's something that our instruments can't even detect? Or does this come down to the point where it's we need to be building different instruments?
I think that's not really solved yet. I mean, you could say, okay, for example, there was a theory which is called supersymmetry, or it still is, where you say, okay, you have certain particles, we can detect them, they interact in some shape or form. However, they don't interact in other shapes or forms. So, and that's where you basically, for example, you have other theories which are the WIMPs, the weakly interacting matter particles. So you say they are there, they interact by gravitation or gravity, but they don't interact with other forces.
Like magnetism or
like
something?
Electromagnetism or other things.
Yeah.
So there's always an idea, but it's basically looking at, okay, let's try something.
Yeah.
So there is no, I mean, when you don't really know what you're looking for, there's never a straight path in science.
Right.
I mean, you just try things out and see what works.
Yeah.
That's basically how all of science works. I mean, unless you have, a new field and the first steps are quite clear sometimes, but usually when you are at a point where you don't know where you're going, you just try things out, which is fine. So absolutely, That's why scientists are paid, basically. Or are being paid for.
Yeah, but I think that sometimes people don't understand that.
Absolutely.
That you need this sort of, people sort of throwing darts into the darkness to hopefully find something to then lead the next step, and that's what basic research is. And I think sometimes people don't understand that, and I think especially, I know, like in Canada, I've said this before on this podcast, but the previous government to the one we have now sort of really heavily defunded basic research.
Oh, that's
because they were just like, well, let's go to something applicable, something that we can use right away, that will make money or whatever. And that was a big thing. But I just I sometimes think that I don't know if people really understand that. And this physics example is a great example, because with dark matter, it's like you really don't know where to go, so you got to just keep trying things.
I mean, my favorite example is that. So when you take the theory of general relativity, Albert Einstein, 1916, you take it and ask people, okay, is it good for anything?
Yeah.
And the usual answer is no, absolutely not. I don't know what it is about. Some people have an idea of, it's about gravitation and how planets move and stuff like that. But we don't need it for anything. I mean, it's just a mathematical game.
Yeah, it's just for these nerds to have fun with.
Exactly. It's basically for all just to keep the physicists happy.
Yeah.
And then I usually take my cell phone out of my pocket and say, okay, without general relativity, or GI as we call it, this wouldn't work properly.
Right.
Because all the GPS positioning does not work without general relativity.
Right.
Because what you do is basically you have, just on a very basic level, you need 3 satellites. You triangulate and see, okay, the signal from your cell phone basically goes to satellite A this long, to B this long, to C this long, and then you try to find where you are.
Right.
However, you are in a gravitational field.
Yeah.
Which and it basically distorts the ways. So you cannot really say the way here. Well, let's make an example. The space basically is not as flat as we think. So. And this is basically what general relativity tells you. And if you don't apply those corrections, I mean, they are pretty minor if you compare them to the scales you're looking at.
Yeah.
But I think for cell phone GPS, it makes a difference of something like 10 to, 15 meters, something like that.
Right.
And it makes a lot of difference whether you're on the right side of the highway or the wrong side of the highway, which is 10 meters. So...
Yeah.
It has a very practical application, a very, very practical application. Everybody uses it.
Yeah.
And if we had not discovered it like 100 years ago now, we couldn't do it.
Yeah.
And there are so many more examples where fundamental science, like 30, 40, 50 years later, actually went into application.
Yeah. But it takes that long.
Absolutely.
Sometimes. And sometimes you don't, most of the time you don't know. Like Einstein didn't come up with this thinking, in 100 years we're going to have these computers in our pocket and satellites and all this stuff. Right.
Or, all the protocols you use for transferring data, for the hypertext transfer protocols and so on, everything basically the internet is built on was not done by Facebook.
Yeah.
It was done by fundamental scientists trying things out. Oh, can we actually do that over such a long cable?
Yeah.
Or can we actually... A transistor, which is basically the foundation of microchips and cell phones and computers and whatnot, people tried out.
Yeah.
Whether it's useful or not.
Yeah, right, exactly. So, and that's, maybe not exactly well, who knows? Maybe the stuff that you're finding here at the institute one day has some kind of application, but this is we're still in the very theoretical.
But I give you another example which is very applicable by now. Do you know Prague? It was a father and son. They got a Nobel Prize 1915, 1916, something like that.
No.
So whoever fact checks, I think it was 1916, but I'm not sure.
We won't hold your feet to the fire on it.
That would be nice. Basically, what they discovered that when you take ions, so for example a carbon ion, and put it into matter, shoot it with a certain velocity, it has a very interesting way of distributing its energy. So usually when you take, for example, photons and electrons, and you shoot it at something, they let's take the tank of water. And you shoot electrons at a tank of water. They lose most of the energy at the surface. And then some of the energy basically goes into it, but it exponentially or so decays. So as you expect, basically you hit it, and on the surface most of the thing happen, and the more you get into the matter, the less happens.
Yeah.
If you take an ion, for example carbon, that's the most famous, it actually at the surface, depending on velocity, you can always calculate that. Not much happens, but at a certain distance, a couple of centimeters usually, it loses basically all of its energy, and then nothing again. And that has been fundamental science, and nobody really cared. Why should we use that? It's a nice finding, but who cares?
Yeah, it's interesting, but so
exactly.
What? Yeah.
So what? Exactly. Of course, it had its applications in other fundamental research, because you could do analysis of, I don't know, crystals and stuff like that. But
sure, yeah. So other scientists could use that.
Yeah. And somewhere I think in the 70s, maybe, again, don't hold me to that too strictly, but there has been, I assume it went like that. I don't know the whole story, but when you have the medical problem, and I assume a doctor talked to a physicist at that point, we have that the tumor in the head, the brain tumor, and if we shoot with electrons at it, we basically destroy the rest of the brain, because let's assume the tumor is right in the middle. Yeah. Well, most of the energy is deposited on the surface, so you basically, yes, you get the tumor, but you also get the rest of the brain.
Yeah. This is like a chemotherapy type. Yeah.
Exactly.
Yeah.
And radiation and chemotherapy. Yes.
Yeah.
And what you can do, you have pull some tricks and say, okay, you shoot from various angles, and then it basically has an interference in the middle, and you get a bit less on the surface and a bit more in the middle and all that. And at some point somebody said, okay, why not use ions? Because on the surface nothing happens, everything happens in between or in the middle, and then nothing happens again. Yeah. And then they did that, and that's actually running very successfully.
Yeah, so you can target that, you can basically avoid the tissue that you don't want to get.
Exactly. You have, pretty much no side effects.
Yeah.
I mean, there's currently the question of fragmentation and stuff like that, but there's certainly much less side effects than conventional therapy.
Yeah.
Which again, it was fundamental science. Now we are curing brain tumors with it.
Yeah, it's amazing. I mean, to me, it was always like, I imagine you're kind of the same way. It's like a fan of science, right? Like we both sort of studied this, got into it. So to me, like, I never thought about having to justify it. To me, it always made sense. You know, there was these applications that we might not find yet. To me, it was also too like this, like getting back to the dark matter stuff. It's just like, why wouldn't you want to know?
Absolutely.
And why isn't it like, this is why I always say to people, it's like, now is sort of the best time to be alive. Obviously, we've got like great progress and things like this, but it's also, you're always, the next discovery is just around the corner, the next big thing, you know. So you're kind of staring into the void, being like, what could be out there? And to me, that should, you know, that's motivation enough. I think a lot of scientists feel that way, but it's nice to be able to have these practical things to sort of say. Yeah. Because that was another topic that I wanted to bring up with you, because when I first got to Germany, I became aware of you and your work and your role here through the March for Science, because you gave a talk at the March for Science.
That's when we met.
We met
and we didn't meet.
We didn't meet there, but I saw you give this talk.
Oh, nice.
Which led me to send you an email.
Oh, nice. Okay.
Yeah, and I know that's one of the functions that you do, and one of the things that you're sort of, I guess we could say, passionate about is communicating science. So you're kind of the first person in Germany that I could really speak to about this, to maybe for people that are listening outside of Germany, what's the sort of level of, you know, it seems like every country is dealing with this sort of, and the US is the big example, because that's where all the media, at least the English media, you get this rejection of science, this sort of, you know, vaccines is obviously the big one, and I know Germany's having a problem with that. But overall, like, what do you think, as being a German science communicator, with the level of, you know, sort of engagement, acceptance, politically and with the public?
So currently, the problem is not as big as in the US or with all the climate change skeptics and vaccination is another thing. Or, for example, in Turkey or Poland, and, just to name a few famous examples. However, when you look at the political landscape in Germany, now we have a party, usually, well, in the polls at around 15-ish%, and they are basically rejecting also the idea of climate change and so on. And if you talk to people, you always have. I mean, I just became a father, and you get in talks with the families, and lots of them are actually questioning vaccination and so on. So we are not in the safe haven, if you like, in the world where everybody believes in science. I think we are not there yet, where, for example, the US is. However, we are slowly taking up speed.
Yeah.
And I believe we certainly should make sure that we, well, ideally stop right away with the distrust in science. However, we certainly should make sure that all the scientists also at some point speak up and say, no, there is a reason we study this for whatever 5, 10, 15, 20 years, and that we actually have a certain expertise when it comes to our topics. Because when you, for example, vaccination is a very nice example. You have all the institutes, the Robert Koch and the in German it's called the Ständige Impfkommission. It's basically the permanent commission on vaccination, which basically analyzes all the data and says, okay, ideally you should do this, this, and this.
Right. For you, like the schedule of vaccines.
Exactly. Yeah. So at the age of X, you should do vaccination Y and Z. Something like that.
Yeah.
And they basically analyze all the data. They're scientists.
Yeah.
However, you always have that, okay, I have the feeling some people have more trust in a mother talking about her story on Facebook compared to we did 5,000 studies with 20,000 children.
Yeah.
So...
Well, I think the trend is that people do have more trust in that.
Yeah, and they shouldn't.
Yeah, they shouldn't.
So they shouldn't, because one thing is data and one thing is a story.
Yeah.
And the story is important, I fully agree, and sometimes the story is sad.
Yeah.
However, it's one of, for each sad story, there are, I don't know, 10,000 good stories. But they are not being told.
So do you think that that's maybe like where sort of the science advocacy or thing is lacking, is in telling good stories or compelling stories even?
I think that might actually be a nice idea of having pro examples, like positive examples of this work because of science. And I think those stories, it's the same in the news basically. When you look at the news, you always have negative news.
Right, yeah.
There's never a story on hooray. Yeah. So this and this happened.
Yeah, this building didn't burn down.
Exactly. So I think that might be one thing. But it's also a matter of trust, I believe.
Right.
So when I gave coming back to the March for Science, I talked about that on stage. So I found out that I was basically, so I was asked whether I want to talk about about science and why science is important. And then I thought, okay, yeah, why not? To be honest, I had no clue what the March for Science is. So I'm not on social media, so I really didn't follow it. And then some reporter called me and, what are you going to talk about on Saturday? I was like, it's Wednesday. I don't know what I'm going to talk about.
Yeah.
I have like gazillion days.
Yeah.
And, but you're so prominently praised. And I was basically after the, what was it? The head mayor, the university president, the other university president, and another university president, and then it was me.
Yeah.
Like, oh shit. I have to come up with some data and knowledge and numbers and facts and whatnot.
You really put the pressure on you.
Exactly, and I didn't know. So they said, I'll do 5 minutes and it should be somewhat funny.
Yeah.
But then I got an email by one guy basically pointing me, the March for Science, you know what kind of people these are, and he sent me a couple of links. And so I looked at these links, and the well, the websites basically said, okay, all scientists are either paid by by big pharma or the intelligence agencies and I don't know what kind of companies. Yeah. So it's all conspiracy theories, evil companies. And to be honest, if some big pharma company wants to support me, I can glad you give me my email address. However, it didn't happen really yet. So also the intelligence agencies are gladly invited to pay me loads of money. So far, it unfortunately has not happened yet.
Yeah, but that's what you would say if they would. No.
Maybe, yes. However, if somebody else wants to pay me a lot of money,
I'm open for funding as well.
Feel free.
If we're doing that, then
exactly.
Let's get that out of the way.
Let's set up an account and share the profits. However, the problem is this does not happen. Of course, if you have scientists at pharmaceutical companies, of course they want to promote their products and so on. However, all the scientists in the public sector, they're hard-working people. I mean, look at all the PhD students working their ass off just to find out something tiny they can use to get their PhD. And
which hopefully, like we were saying, 50 years from now may be part of something that
exactly. But that's not what they're doing. They're not looking at in 50 years that can be applied.
No.
They're doing it because it's fun.
However,
at some point we put as much trust into people saying no, all science is bullshit, and they don't even do science.
They have no experience with
no experience whatsoever usually, as compared to the people who are actually doing it for 10, 15, 20, 25 years. I think that's
troubling.
That is troubling. We should. I mean, when my car breaks down, I don't go to somebody. You never repaired a car. Maybe want to give it a try. I go to an expert, and that's basically what we also should do when it comes to science. And currently, we're going to the mother on Facebook.
Well, but I think it's important. I mean, because it gets kind of frustrating, I think, for people in our position that sort of work in this area, because we can say these things, right? But there's. And this is something that's come up in a number of different podcasts. Is like the thread has gone through this, in which the first one I did of these, I talked to a guy who he's pretty well known in Canada. He was on TV in Canada doing science shows for decades. And then I talked to my PhD supervisor, right? And the motivations, are the conversation was definitely different. The guy who's worked in media is like, you can't just beat people over the head with these sort of facts or these sort of things, right? And then you talk to the academics, and it's like, well, why do you do science communication? Why do you think it's important? Because I want to promote evidence-based thinking and policy and all this stuff. And there's a real conflict here, and then it's like the message isn't getting through, obviously, and there seems to be some sort of even just like fundamental reluctance that if you tell people this, even if we tell them, the car thing, you wouldn't take your car to it. They'll find a way to be like, well, yeah, but that's different, or this or that, or So it's just, as I'm talking to different people about this, this same thing sort of keeps coming up, and it's just like, I don't know what the solution is.
I don't know either.
Right.
So I think one of the things science communication has done wrong in the last, decades, if you like, we talked lots and lots about the findings. So we found new particles X, Y, Z, and we have found a new way of doing this. And however, we didn't talk in my book enough about the way of doing science, the way of thinking,
the process,
the scientific process. We did not talk about that enough. We certainly did, and some people more than others. However, I think the way of a scientist to think is much, much different from a non-scientist. And it's basically you have, if you look at politics as an example, people try to find the arguments basically to fit their ideology, if you like. However, as a scientist, you're trained to, okay, these are the facts. What is the next step? And what's
the possible meaning or conclusion?
And okay, I thought it might be that, but now we have two more facts. It cannot be that anymore, so we have to change our thinking. You're always adapting. And this has not been done. This way of thinking has not been promoted enough, I believe.
But I wonder too. I mean, like at some level, I mean, we should talk to a psychologist or something too about this, because on some level, I think there is like people have, their position, their idea, and the idea, the thought of sort of saying no, I was wrong, is like an emotional process to them. Like it's somehow admitting, I was wrong. I'm, either not intelligent, or I don't know what that motivation is, but it feels like people intertwine their thoughts about the world with their personal self. And so rejecting one is sort of like an attack on the other.
Yeah, but it's not.
Yeah,
so
it's not. I know that. You know.
That's a problem. I had that in the lecture. So I gave a lecture that was actually a very eye-opening experience for me. So I gave a lecture. It was on theoretical nuclear physics, and it was on a certain principle. It doesn't really matter now. And in physics, there is basically, so it's called the Lagrangian equation of motion. So it's basically a mathematical machinery. You basically plug in what we call a Lagrangian, so it's basically one equation. So the basic concepts of all the interactions and fields and whatnot you want to have. And then you plug it into a certain machinery, and you get a result, equations of motion, and then you compare to experiments. That's a very easy way of describing a PhD thesis, basically.
Yeah.
Usually it takes a while,
and
it has a certain supercomputer in the middle. But that's basically the idea. You have a very well-defined mathematical process. You plug something in, you get something out, you compare to experiment.
Yeah, to see if they match up.
Exactly. And if it matches up, maybe we did something right in the beginning. If it doesn't, maybe we did something wrong in the beginning.
Yeah.
But in the end, it's basically a game of guessing.
Yeah.
Of course, it's educated guessing, because there are certain symmetries in the world which we should, plug into it. We have certain particles we know that they are there.
Yeah. You're using existing knowledge. That's
you have
been
previous
tested.
knowledge, exactly. Which sometimes you can say, I don't believe that, and try something out. That's fine. That's science.
Yeah.
And I was giving that lecture. It was to, I think, 8 semester students. And I said, okay, I have that Lagrangian, and I plugged that in, and then I said, oh, where did you get that Lagrangian from? I said, well, I basically just, I didn't say that, but I pulled it out of my ass. So I just thought about that, and let's try it out. But you cannot do that. Why can't I do that? Because it's not written in the book. We don't know whether it's right or not.
Yeah.
And then it was an eye-opener for me, because that whether it's right or not, we'll find out in the end.
Yeah.
But not in the beginning.
Right.
So there is no right or wrong here. It's basically trying out what works and what not.
Yeah.
So, and they were basically physics students close to their master thesis.
Yeah, okay.
And they did not know how the scientific method works.
Yeah.
Of trying things out, comparing to experiment in our case, and then judging whether we did something which was worthwhile or not.
Yeah.
But they did not know, because, and then I basically interrupted the lecture and talked to them about, why are you thinking it's not right?
Yeah.
And they always had that, okay, in our textbook it says we have to use this and this. It was very schematically.
Yeah.
And the way of teaching they experienced, I mean, there are good and bad teachers, but the way of teaching they experienced never taught them how to think scientifically, which is a shame, close to physics masters.
Yeah, well, and I've thought of that too, just like as, a possible, when thinking about possible solutions to avoid this sort of situation where nobody believes your doctor or your expert, whatever, is that maybe you have to, like, rather than trying to convert the people that have already just made up their mind, you need to go a generation back and look at how we're doing education.
Yeah, absolutely.
And that's part of it. I mean, then there's obviously the politics of trying to reform the school curriculum and stuff. But I think it's like, when you think, this idea of the scientific method, and, people haven't been taught that, to me, I often think about, like, children. You watch children. You said you're a new father. You watch how they learn how humans learn when they're growing up. It's trial and error.
Absolutely.
And that's so it's almost like the scientific method is like it's intrinsic in
Absolutely
in how humans have evolved.
Usually people say children learn much faster than adults, and that might be true. However, in my mind, the main reason why children are much better in learning than adults is they don't give up.
Yeah.
I mean, if for example I just take by snipping I take away the power of walking, and you cannot walk, you just lie down.
Yeah.
You would try to get up and you cannot because you don't know how to.
Yeah.
And you do it again, and then after like 3 or 4 times you say, screw it, I just get a cab.
Yeah.
And somebody picks me up, but a kid tries a 4th time, a 5th time, and a 100th time, and a 1000th time.
Yeah.
Because that's how they do it.
Yeah. When they know nothing else.
Exactly. Yeah. And they just try, and they are not afraid of error. Mm-hmm. They just try things out.
Yeah.
And if I fall again, then I fall again.
Yeah.
Which is beautiful.
It is. It really is. I mean, it's the persistence that they have, but and again, like not knowing anything else, they have no preconceived notion of, well, this should work, this shouldn't work, or I've been told this, I've been told that.
And it basically all breaks down in school.
Yeah.
And the current way we are basically living and doing school is, I believe the first, this, especially in mathematics, for example, this is wrong. Of course, there is right and wrong in mathematics, but why not say, you're saying 3 and 3 plus 3 is 7. Why do you think that?
Yeah.
And then get into the discussion instead of saying, no, it's wrong, it's 6. Everybody knows that.
Yeah.
And this is
this is the book, it says
exactly.
It's 6. Just,
repeat
this.
Repeat after me.
Yeah.
Instead of saying, okay, why do you think that? And basically trying to figure it out with the kid. Of course, I mean, if you have 20 kids with you as a school teacher, that's a lot to ask, but especially when raising a kid, why not just say, let them try out things? And I mean, there's a famous example by Neil deGrasse Tyson when I said, if the egg breaks, it's 20 cents.
Yeah.
What is it compared to the future of your kid?
Yeah.
So
exactly. Yeah. So, I mean, obviously, like you kind of mentioned there's an issue of time and everything
absolutely.
Like that, but I feel like that's easily overcomable if people put a value on that. If people decide that, hey, you know what, which when you think about it, teachers play such an important role in society and generally don't get the recognition or
absolutely not,
or the pay for it. So if you make that sort of, if society decides, and I mean, then you have to. Obviously, it's not as easy as that.
It's absolutely not.
But it's I think that's a step, and then something we kind of talked about a little bit before we were recording here is just like and it came up, I think, is telling the stories behind the science, but also the people behind it.
Absolutely. Yeah.
I mean, I think that's an important thing here. I mean, we can, that's what I like doing with these podcasts, because you talk to people, that are scientists, and you see that, oh, hey, they sound like me, they might.
They look like me.
They look like they might, curse every once in a while, like this kind of thing.
They certainly do.
Yeah, exactly. In my experience, I always say to people, it's like, if you have gone to any scientific conference, you'll see how normal these people really are when the open bar opens up.
Yes.
So I think that's a thing that could also be done, but it's I don't know. It seems like it's a bit of an uphill challenge, because a lot of science engagement stuff, and I wonder, you've, and we can jump to this as well. Your what's it? Sorry, the name's escaping me now. The Science Birds, yeah. Yeah, so it's sort of a live thing, but it's how much of the audience is already, you're already sort of preaching to the choir. Like the people that show up to these events are already.
It depends what we are doing. So we have various programs. So for example, I run a program which is called in German Wissenschaft zum Anfassen, which is hands-on science. And we take some exhibits on certain physical phenomena, so nothing major. Nothing major is maybe not the right term. So we have particle accelerators with us and stuff like that. But
sounds pretty major.
It is major in a sense. But we also go to primary schools.
Yeah.
And we talked to them. What do you think science is? How do scientists look like? And when you start, I mean, I have a 100% success chance so far. When you ask a primary school kid, how does a scientist look like? You always get the white coat.
Yeah.
In the beginning.
Yeah.
And I never wore a white coat in my life. And I still consider myself a scientist.
Yeah.
So, and many scientists never did. So, and then we do like an hour or two of playful science, and we let them experiment, and we never tell them, okay, this is how it works and you should repeat this to get to that result. But we ask the question, sometimes we just go to an exhibit and say, what do you think it is?
Yeah.
And they have no clue because they cannot. Because they have never seen a superconductor or something like that. Because, well, most people don't do that in their physics studies. But then we ask the right questions and we let them experiment. And sometimes it just doesn't happen.
Yeah.
So, well, it just doesn't work, and then we do something else. But it's basically, they don't have any pre-knowledge of science. So we are basically forming their way of thinking about scientists. So sometimes you have, when you, for example, go to in the school, to what we call a Leistungskurs. It's how would you translate that?
I'm not sure.
So basically so in Germany, basically in the end, you have to select 2 subjects which you're doing very intensively.
Okay.
And before you do your degree in school. And the people choosing physics, obviously, they know about physics and they want to do physics and potentially want to study physics. So then it's also a bit of preaching to the choir, but then you get into completely different discussions. Then you get the discussion of, okay, how do physics studies really work, and what is it really to be a scientist instead of what we see in TV, for example. And in other projects, for example, when we do the same exhibition and we go to the Hessentag, it's we talked before we started.
Festival.
State festival, 10 days, everything between bratwurst and political affairs. And there you have like 20 to 30,000 people coming to the science area and experimenting with us, and they have no clue whatsoever is happening. So it's basically a good mix of people who already know about what we're doing and just getting a deeper glimpse into it, or basically people having their first contact with science.
Right, and so it's all about making yourselves visible to different audiences, and then sort of tailoring the sort of questions in the program to it. Yeah, I mean, that's one of the things I think back home in Calgary they did, and I mentioned it during the workshop that you put on, is this science festival that they do every year, this Beakerhead Festival it's called. I haven't seen anything really like it, and to me it's a really great example of this, where you're just like, look, we're going to make it visible so people will see it, and and it's and the point, the goal is not necessarily to teach a predetermined fact. It's like come and interact with the thing, and
ask a question and so on.
Which I think people really enjoy. I mean, I think
absolutely.
People like to discover things. They like to see it in action,
and then they like to talk to scientists. Because I had that was actually quite funny. There was one lady, it was quite a while ago already, but it was basically my favorite conversation I ever had at these events. So I explained what particle accelerators are and what you can do with them, because she always asked and wanted to know what can you use it for and so on. And in the end she said, yeah, that's very useful and you really should keep doing that. Actually, who's paying for that? I mentioned, well, basically it's you. I mean, it's all taxpayers' money to a very large degree, so it's basically you. Oh, right. What can I do that you get more money? And basically, she came in from having no idea what science does at all to, oh, this is really important. What can I do to support you? Which is actually quite nice. I mean, that was like half an hour, 1 hour conversation. Which is, when you look at the scales, other science communication methods, like, I don't know, a blog or newspaper articles, they reach like hundreds of thousands people. However, not in that depth.
Yeah, not in that personal.
Exactly, and you need. I think the mix is it. So of course you need all the science blogs and the newspaper, but you also need scientists getting out, being visible, talking to people why this is important.
Yeah, I agree. I mean, so I kind of mentioned that I was the group in Marburg sort of approached me to talk to the grad students and maybe develop a project for them, and they all had the idea of we could do a video, we could do a podcast, YouTube, and I was kind of like, you know what though, I think these live events, I was kind of trying to maybe plant that seed, because it's like I think those are some of the best, and if you put yourself in a situation where you are gonna get, and that's the right, you need the right conditions, like in Hessentag Festival is a great one for that, because people are just going to be walking by and see it. That's really good. And then so the science bird thing is this. How does that? What's that about?
That's basically a conglomerate of people. So I did a lot of science communication always as a hobby project. Basically, I do a bit of the institute, but I also run talks. For example, I run a program which is called Physics in Hollywood, which is quite popular by now. It's basically the idea is, does the science in Hollywood movies work?
Yes.
So, for example, if James Bond does this and that, does it actually work? Or when Spider-Man saves Mary Jane with a spider web, does it actually work? And so on and so on. Star Wars, lightsabers.
So you're ruining movies for people.
Well, sometimes it works as well. So also you don't really.
Some get it right. Yeah.
I try to tell a story of, the string of things that don't work, and then surprisingly something works, and it's always 80% comedy, but it's also 20% science.
Yeah.
So the idea is, and it actually made it to theaters and stages all across Germany. But the idea is basically tell a nice story, have a good laugh, but in the end there are equations. So people actually, they pay good money to see a physics lecture.
Oh.
So it's basically in the end...
In secret, like it's disguised.
It's a disguised physics lecture in the end. Again, it's 20%, 80% is basically commenting movies and doing that. But in the end, that's my approach, if you like. In the end, I always explain scientifically what happens, and with equations. And I run it from schools to companies to theaters. And especially in schools, the feedback is always like, we are glad that you also really explain stuff. So that's one of the main things I do. I run an experimental show, which is called, together with a colleague, which is called the Quantum Mechanics, which is basically the idea is I am the theoretical physicist and my colleague is the experimental physics, so the quantum and the mechanic.
Okay.
So he actually also comes in a mechanic outfit. And then we basically blow up things on stage.
Which people love.
Which always works, so it's always fun. So, but it's always explaining things.
Yeah.
And so I ran a bit of things. Some other colleagues actually ran courses on science and science communication and other stages like Science Slam. And so we basically all put together a project which is called Science Birds, where we basically offer everything. If somebody wants to have X, Y, and that, they basically approach us and we see what we can do.
So it's like tailor-made sort of events.
Exactly. So you want the last thing that was actually fun. We had a funeral slam.
Whoa.
That was fun. It doesn't sound like fun, but it was fun. So there was how would you call it? It's the graveyard gardeners of Frankfurt contacted us by some contacts. I think went a couple of loops, and they had the problem that not enough visitors are coming to the graveyard, which in Germany now, as I learned, is a big problem. Because people, I mean, you think at some point everybody has to visit, but it's not the case because there are other options where you can actually bury yourself. And they have something like a day of the open door, and which doesn't sound too fun at a graveyard.
Yeah.
And they wanted to try things out, to have new concepts, new formats to reach people. And they saw we doing that science slam thing, and they approached us. What can we do to make graveyards more visible and more interesting? That a younger generation actually comes and visits and actually thinks about death in a sense.
Yeah, and the role of the graveyard.
Exactly, and usually the visitors are, let's say, 70 plus.
Yeah.
And they wanted to have visitors more like in the younger age region. And what we came up with, there was it's called the Funeral Slam. We invited a couple of preachers and people speaking at funerals.
Okay.
So, professionals.
It's
funeral. I don't know what the English term is.
I'm not even sure. I know what the
Trauerredner in German, but
I know there's an English term. I just can't think of it right now.
So basically, people giving the last honors at a funeral, not preachers. Sometimes they're preachers, sometimes not.
Yeah.
And however, we said, okay, we give you people like 2 weeks or a week in advance, and you basically give us a speech on this person. For example, one person who died was Batman, or James Bond, or Goethe, or who else died? People like that. Marie Curie actually also died again.
Right.
So we said, okay, we mix basically fictional characters. Homer Simpson, he died. Fictional characters and people who really died at some point, but it was a long time ago, so nobody's really affected anymore. Yeah. And then we let them give a speech on these people. Yeah. And then the audience can vote which they like best and so on. So it was actually really, really funny and very well made. Yeah. Because you had professionals thinking about, okay, how can I let Batman die? Or James Bond. And you had a room, we had roughly 200 people. That was the maximum capacity of the hall. Yeah. We did in the main funeral hall of Frankfurt. And, people thought about death and funerals in a different way after that. Yeah. So things like that, we're doing also other things. So everything that's fun and scientific in some shape or form, we do.
Wow, that's great. And do you have a website or anything?
It's sciencebirds.de.
.de.
Okay. Yeah, we're German, so sorry for the pronunciation as well. If you get that far, you probably realized.
yeah, I think so. Yeah, well, that's really cool. I mean, we've been going for about an hour here, so it's usually about the time where people start to get tired. Yeah, but if you're doing okay, we'll keep going a bit.
Yep, yeah, I'm here.
Because I wanted to. I mean, I'm a little torn now as to where to take this, because I got a couple more specific science things. Something at the specifically here at the Institute. One of the projects that caught my eye was the supercomputing project. Okay. So I was wondering if you could talk a little bit about that, because how is it described? Exascale?
Exascale?
Yeah. Do you know this one?
I think that is that the physics one?
I think it was. Yeah, I think it was in the physics. Exahype.
Oh yeah. That's the gravitational wave people.
Yeah. So it seemed to me like they were designing or wanted to use supercomputing to map like these really complex systems, like earthquakes and blood in your body and this kind of stuff. But my question really was just like, this isn't what they're working on, because I didn't really understand it. So this is not really working on a hardware advance. It's like a software, like algorithm sort of.
Yes, so we're looking at it from different angles. But we have one person actually doing it from an implementation point of view, so hardware. Mm-hmm. So one of the main things actually being developed here, which is actually quite application based, which is fun for institute doing fundamental research, but it went into application very fast. Was basically building supercomputers from standard components. Okay. And which is nothing new in a sense. However, the implementation is the interesting part, and the cooling.
Right, keeping the components cool.
Exactly. The one thing you have to do with the one big problem with computers is, I mean, building a supercomputer is easy if you have an infinite amount of space
Yeah.
and an infinite amount of energy
Right.
to cool it and to power it.
Right.
That's easy.
Yeah.
So everybody can do that. You just go to, I don't know, whatever your favorite website where you order stuff and order like 2 billion GPUs, CPUs, whatever you want to have, and plug them all together.
Yeah.
The challenge nowadays is basically to have computers which are, with a given amount of energy, as efficient as possible.
Right.
So that's where, for example, the Green 500 list comes in.
Right.
Most of the people know the top 500 list with the fastest supercomputers,
Okay. Yeah.
which is a feat in itself. But as I said, if you have an infinite amount of resources, pretty easy.
Yeah.
However, to build it as efficient as possible in a certain amount of space and certain amount of cooling power and so on, that's basically the challenge nowadays.
Yeah, because I think I actually wrote a piece this year about some new sort of computing thing. It's not the point. But the thing that popped out at me when I was doing research of that is that the computing sort of industry, or like, not industry, but like all of us using computers and using all that, takes more energy and has a bigger carbon footprint than the aviation.
I can imagine.
Yeah,
absolutely.
and that's what the
Absolutely.
scientists there were telling me, and I was like, I don't think people really realize that. Yep. You know, the amount of power that we use with our computers and
Absolutely.
stuff. So that's sort of what this project is kind of.
Exactly. So
one of the components.
The person doing that is actually developing systems which are as energy efficient as possible, but still are supercomputers. So of course, I mean, the most energy efficient computer is none. So, but still doing computing on a supercomputer level. So, for example, the GSI, which is a big particle accelerator complex just like 20, 30 kilometers south of here, they're using one of these supercomputers to basically have their data processed.
Yeah.
And the big new thing about at that time was the cooling. So we have the water cooling, but not close to the components, but within the doors. Which then you can build a huge water circulation, and it's very energy efficient.
Yeah. So
that's basically done on the hardware side.
Right. So is it more? Yeah, it's more about finding clever sort of engineering fixes to cool and
but
build
then
these things.
The other side is, and that's where for example, the Exahype and all the other projects here come in, is basically on the algorithms.
Right.
So what can I do? Again, if I give you infinite amount of resources, you can write the shittiest code you've ever written, and you still get a result in 0 time.
Yeah.
So because you have infinite amount of computing power.
Yeah.
However, if I say, and that's where scientific computing power, but in all other areas as well, is you basically write now proposals for computing power. So instead of saying, I want, I don't know, 10,000 euros here, you write, I want to have as many computing hours on this cluster. So it's basically a big national thing, and it's a competition who gets computing power nowadays.
So there's a real,
it's a competition.
Yeah,
so, if you have a good project, there's usually scientific evaluation.
Yeah.
And that's basically where it becomes interesting. And then it becomes, okay, if I have, I don't know, 10,000 hours of computing time, of course, spread over all the processors and GPUs and whatnot, then you want to make sure that you use them properly.
Right, efficiently. Yeah.
Efficiently, yes.
Yeah.
And
you don't want to waste your time.
Exactly, because you only got as many as you applied for. So your code has to be stable, and it has to be well made, and it has to be parallel and so on. And that's basically a couple of projects here at the Institute even. So we had a physics code, which was written in, I don't know, the 90s. I actually did my PhD with this code.
Okay.
And at that time, actually, I basically not started it, was a very small part in that. So we had one routine. That's basically one of the codes simulating heavy ion collision. So coming back to the very beginning.
Right.
So we take gold on gold and we smash it together, and I wanted to look for a certain particle, how it tracked through the collision, and that was very computational heavy at that time.
Yeah.
And there was an old routine which figured out how it can be done. And so I looked at it, and I'm not a good programmer at all. However, I looked at it, it has to be done more efficiently.
Yeah.
And I wrote a program with a little help of a friend who's an IT guy, and it actually was faster by a factor of 100. Which is not because we are so good, because in the 90s this was state of the art.
Yeah.
So, but just by writing it again, it became faster by a factor of 100.
Yeah.
This small routine. And here at the Institute, some people sat together and said, okay, what can we actually do to have the whole program run faster? And then some IT guys looked over it and parallelized it, and roughly 3 years later, the whole program was faster by a factor of 100 or 400, depending on what you look at.
Yeah. And that's just by having different groups of people looking at it, refining it,
by working interdisciplinary, because I mean, physicists, whenever a physicist programs something, you can be absolutely sure it works.
Yeah.
It will be shitty code, but it works. If you have an IT guy looking at it, it will be nice code, it will be efficient.
Yeah.
Whether it works or gives a result is not really important.
Yeah.
But combining those two powers basically then you have an efficient code, which actually produces results.
Yeah.
So
and the specific results that you are looking to find.
Exactly.
Yeah.
So which is a nice idea.
Yeah, that's
also part of the exercise where you basically find ways of certain physical problems on supercomputers.
Yeah. Well, and it seemed like that was a really one that kind of stuck out to me when I was, just perusing through the website and stuff too, because you have the neuroscience stuff going on, and then also some of the economic stuff that you said, and then there's the supercomputing thing, and I mean you can see the links right there of how in neuroscience, mapping brain and artificial intelligence and all this kind of stuff, you're going to need these computing power.
Absolutely.
Yeah. So, and even then in the economic stuff, I think it was about predicting risk and everything like this. You
can imagine risk analysis.
This is going to take, loads of computing power. And like you said, if you had all the resources, then it wouldn't be a problem.
But you don't.
Yeah, exactly.
It's very simple.
And I think it's a good point that you made, that it's like, bringing the people who need the algorithm, who need the results, and talking to someone who actually does that. Because I noticed this too, just in my PhD, when I was working in genetics. So you would have to have, small programs to search through databases or whatever it is, And I think every grad student has this problem. More so now, they all have to kind of know how to code in R or Python or something like this. But it's like you said, they're just trying to get the result. Like, they don't care about the code. They don't care,
It doesn't have to be maintainable. It doesn't have to be efficient and so on.
And if you're the student that gets that from the postdoc, Pat, this is what I use. Just use it.
Don't ask questions. Push the button.
Yeah, exactly. So it's not the best way. But and I think it's something that I think people don't think about, is like, because we're like, oh well, quantum computing. If we do these things, then we'll have all the. But it's like there's probably a lot of value in just removing the waste in some of these things that we already have. So it's cool that there's a project doing that.
There was a nice initiative. I read about that. I didn't follow it through, but I think it was an astrophysics professor or postdoc or I think it was an astrophysics guy, let's call him that way. And he said, okay, the programs we are using to actually do the analysis we are doing are from the 80s.
Yeah, that's...
So I refuse to keep working when we are doing that.
Yeah.
So we are talking about developing next generation stuff, but we are using programs which are working for more than, I don't know, we are alive.
Yeah.
So I always said, okay, you cannot use a program as a joke. I use programming languages where the compilers are older than I am.
Yeah.
So,
doesn't make sense.
That doesn't make sense.
Yeah.
Exactly.
But this kind of goes to like sometimes, everybody wants the fancy new technology, right? But not thinking about these sort of things.
Yeah.
It's like, just give me the faster computer,
exactly,
and I'll still write my shitty code on it. And
exactly, like, well, but if you have a shitty code and a fast computer, the code is still shitty.
Yeah.
so just if you can actually make sure that you use it on a laptop, if you have somebody look over your code who actually knows what he or she is doing, please do so.
Yeah. One, and I know in the genetics area that they actually brought in a bioinformatics professional to work in the department, just for these kind of things, right? Like, who it's like, so he's a little, bioinformatics is obviously computing, but for biology specifically. But it was just like, and it seemed like, just like a no-brainer. Why hadn't we done this 10 years, 5 years ago, 10 years? This is a guy that can just infinitely speed up all of these projects that people are working on.
There's internal problem in the system, I would say, because this kind of work is in the current scientific system we have, at least in Germany. I don't know how it is in other places. It's not really rewarded. Because if you have the standard scientific career, basically you do your studies. I take again physics as an example. You do your studies, you do your PhD, you do the postdocs 1, 2, and 3 maybe, and then you apply for faculty positions. Done. And you always stay within your narrow topic and hope somebody think it's fancy.
Yeah.
But if you actually, we had a couple of people. That's also a small problem at the institute here. So being an interdisciplinary institute, you cannot be as interdisciplinary as you want, because if you produce PhD students, so produce in the sense of graduate them, and they are interdisciplinary, they just won't find jobs in science.
Right.
Because the scientific culture is still monodisciplinary statistically.
Yeah, definitely.
So that's a big problem. I mean, if you, for example, take biophysics now is pretty much accepted, but if you take somebody who works in various let's say optimizing codes for physics, just staying in that example. In the IT world, in the computer science world, he's basically like, okay, you are just doing the footwork for somebody else. You're just like you deliver a product. You're not doing science. But in physics, you're the IT guy.
Right.
So, but you're actually doing relevant science and progressing basically on the crosslink.
Yeah.
But if you actually want to have a job, it's still very monodisciplinary.
Yeah.
Which is something we have to change.
Yeah, I agree. I mean, I think a lot of people even face this problem when they're looking at, okay, I've done a PhD, I've done graduate school or whatever, and I know that I'm not going to go into research or academia. It's like they feel like they have no skills for any other job because they've been so trained, and it's not necessarily true. I mean, you do gain skills along the way that you can then market, but it's getting people within science, I think, to respect that we all, the grad student has learned all these different things and should be, like you say, like encouraged to like be interdisciplinary. Yeah, but I wonder if that's changing though. I kind of
slowly.
Yeah.
But I mean, if you look at now you can actually study bioinformatics, as you said.
Yeah.
You can study biophysics. You can study neuroscience in some places. So it's slowly changing, but it takes a while.
Because it feels like it's one of those things that you always see in like press releases or like these kind of things where they're trying to promote science. When the institutions, they're like interdisciplinary. It's like the word that's thrown out all the time.
It's a buzzword.
Yeah, exactly. Yeah.
But it's still a big problem that you should encourage it more, but you also should live it basically when you hire people.
Yeah.
Which is unfortunately not done as much as we should do it right now.
Yeah, people aren't walking the walk. Yeah. Well, I mean, I feel like we could probably go on and on and on, but let's cut it off here, and we should do this again.
Absolutely.
And I'll say thank you again for having me down to the Institute and agreeing to do this. It was a great discussion. If you have any sort of websites or anything, you gave the sciencebirds.de.
Yes.
If there's anything else, that you want to let people know.
Currently, it's sciencebirds.de. Have a look at Physics in Hollywood. That is usually great fun. It's also available in English.
Okay, cool.
There's a German version on YouTube, but I don't know whether the English version is up yet.
Okay.
So we're currently working on the social media stuff.
Right.
But apart from that, thank you for having me.
Yeah, no problem. That was great. All right.
Thank you.
We'll leave it there. And there we have it, friends. Another conversation episode done. Another great conversation, if I do say so myself. I really enjoyed speaking with Sasha. I hope you enjoyed listening. Like I said in the intro, I think he's just a really interesting guy. Very engaging guy to talk to if you get a chance and you're in Germany to see him. I recommend you do, for our German listeners, although he does, I believe, tour the Physics in Hollywood internationally. I don't know if it's made it to North America yet, but definitely in Europe. So if you're listening from any of our European countries, go to sciencebirds.de, check it out. And yeah, just a big thanks for having him on. Can't wait to do it again. If you want to give the show a follow, please do at 2brad4u. That's on Twitter, Instagram. You can follow me on Twitter at bvanperdon. Our website, 2brad4u.wordpress.com. You can go there, check out all the episodes, show notes to some of the shows, links, that kind of stuff. Thank you so much to the Freak Motif for allowing us to use the music. I can't think of their website right now, so Google Freak Motif and go there. You'll find them. They're great. They're on Bandcamp and SoundCloud, I believe. Sorry, boys. I dropped the ball on that one. And then Sebastian Aboud. SebastianAboud.com. Check him out. Great graphic designer. Living the life out on the west coast of Canada, Vancouver Island. He did the artwork for the show. He's a big help. He's helped me out with any sort of logo thing that I've ever needed for any of the podcasts that I've done. So he's been a big supporter since the beginning. So always want to shout out to Seb. And if you haven't checked out my other podcast, Cast of the Unplucked Gems, it's also on iTunes, Stitcher, all those great places. Podcast dedicated to going album by album through the catalog of the Tragically Hip, the great Canadian band, the Tragically Hip. Gotta promote that because I am honestly just having such a blast doing it, as I am having such a blast doing these conversation episodes. We're hoping to get some more queued up for January, and we're hoping to find my co-host Brad and get him back in here for at least a year-end special, but we'll see what we can do. So until then, thank you always for listening, and have a good one, and we will see you next time. Bye now.